In the past, when we were looking at simplifying some expressions with radicals, one of the things that we said we didn't really like was to have in our simplified solution a square root in the denominator. It's fairly common to ask people to change things so that that radical is no longer expressed in the denominator. So what was the way that we did that? Well, for example, here, and if it makes you think things a little bit better here, if we're dividing square roots, we're just dividing things inside their square roots. So square root of 5/8 is the same as square root of 5 over square root of 8. And if we didn't like a radical in the bottom, one of the things that we did was we wanted to multiply by another square root of 8. And the purpose of doing that was that would give us a perfect square. We did that on the bottom and the top so that it was like multiplying by 1, so we haven't actually changed the fraction. And we kind of did this multiplying square root things when we did that before. We multiply what was inside, so up here the square root of 5 times the square root of 8 is the square root of 40. And on the bottom, the square root of 8 times the square root of 8 is the square root of 64. And then by design, because we picked things well when we did our multiplication, the square root of 64 is actually 8. I can actually take that square root and I'm left with the square root of 40 over 8. So in that way, we're able to get rid of the square root out of the denominator by cleverly multiplying by the square root of 8 over the square root of 8 in order to get rid of that denominator. Again, this answer isn't quite done yet because if you recall, 40 has 4 in there, which is a pair of 2's. So we should break up that square root of 40 to be the square root of 4 times the square root of 10. Just kidding. Over 8, which is 2 square root of 10 over 8. And now that the 2 and the 8 are both outside the radicals, we can reduce those. So your best final answer for this is going to be 10, or root 10 over 4. Again, what we were trying to do and our goal in doing any change at all was the fact that we didn't like the square root in the denominator. Well, what happens when we end up having pluses and minuses in the denominator as well as radicals? We still have this dream, I guess, of wanting to make sure that we don't have a square root in the denominator or cubed root or whatever. We're just going to be really focusing on square roots here. But we want no radical in the denominator. So what are we going to do? Well, a couple of things. Let's try a couple of things. Before, what we did is we just multiplied by whatever was on the square root on the bottom. So let's see what would happen here if we multiplied by the square root of 5. In this case, because we have the square root of 5 times plus 1 times this, you'd have to distribute through. And when we do the square root of 5 times square root of 5, that would nicely give us the square root of 25, which is great. But then we'd have plus 1 times the square root of 5. And guess what? Even though we can take the square root of 25, we're left with this, and we haven't actually gotten rid of the radical. So if there's a plus or a minus, our old tools aren't really going to work to help us in this case, because just multiplying by what's inside the radical is not going to work. So the next question you might ask is, well, what if I multiplied by exactly what's inside the radical? So like in this case, what if I multiplied by the square root of 5 plus 1 times the square root of 5 plus 1? Well, that seems pretty reasonable. However, if you do your FOIL here, notice we're going to get the square root of 25, which is a perfect square. That's good. Plus radical 5, plus another radical 5, plus 1 on the bottom. And when we do that, we end up with the square root of 25 is 5, radical 5 plus radical 5, 1 plus 1 is 2 radical 5. Remember, same root, so we add the numbers that are in front, plus 1. And I still have a denominator with a square root in it, because this is what my new bottom would be. And that doesn't help me at all either. So multiplying by exactly the same thing on the bottom doesn't work. Multiplying by only what's in the square root doesn't work. So instead, what we're going to do is, if there's a plus or a minus, there is still a way to multiply by something clever. What we want to do is we want to multiply by what's called the conjugate. And what the conjugate is it's the same number values, but a different sign in the middle. The point of doing it this way is that those middle terms will end up dropping out, because you'll have one that's plus and one that's minus. They'll cancel out. And then you'll actually be left with just the perfect square parts of it. All right, so let's see what that would look like here. Here we have 3 over radical 5 plus 1. So because I have a plus and a radical, in order to get rid of it, I'm going to multiply by its conjugate. The conjugate of square root of 5 plus 1 is square root of 5. Instead of plus in the middle, I'm going to make it minus 1. if you do something to the bottom, because I want to multiply by 1, I also have to do that same thing on the top. Okay, so let's see what this does. On the top, I have 3 times radical 5 minus 1. I'm going to have to distribute that through. So 3 times radical 5 is 3 radical 5 minus 3 times 1, so minus 3 on the top. I'm not worried about the radical 5 that's now in the numerator. I don't care about that. What I'm worried about is the radical in the denominator, which is what I'm trying to get rid of. Now on the bottom, I'm going to try to multiply out this. Now here I have a binomial times a binomial. I've got to use FOIL. So when I do the outsides, radical 5 times radical 5 is radical 25. When I do the insides, radical 5 times minus 1 gives me minus radical 5. When I do the insides, 1 times radical 5 gives me a plus radical 5, which is awesome. And then here I have a 1 times a negative 1, which gives me a negative 1. So the nice thing with choosing this for my FOIL, because 1 was plus and 1 was minus with everything else exactly the same, I end up with a minus and a plus term that are the same and cancel out. So on the top, I still have 3 radical 5 minus 3. On the bottom, I have the square root of 25, which is 5. These terms, which negative radical 5 plus radical 5, which is 0 radical 5. And then I still have the minus 1. And I can do 5 minus 1, which is 3 radical 5 minus 3 over 5 minus 1 gives me 4 on the bottom. And this would be my most simplified expression and term for this division where we have radicals involved in my expression. All right, so it definitely looks a little bit weird. We do need to still check to see if we can simplify our final answers when we're done. Let's look at a couple of other examples and kind of see what comes into play here. So for this one, we have a radical in the denominator. I don't like that for my final expression. So what I'm going to need to do is multiply by the conjugate. Oops, sorry about that. Multiply by the conjugate of the denominator. Right now it's 3 minus radical t, so my conjugate is 3 plus radical t. And if I do that on the bottom, I also have to do it on the top. Okay, so on the top here, I'm going to multiply. There's one number times a group, so I'll have to distribute. 8 times 3 is 24, plus 8 times the square root of t is 8 root t. In the denominator, I'm going to have to do the whole FOIL thing. 3 times 3 gives me 9. 3 times a plus square root of t is 3 plus root t. 3 times a minus root t is a minus 3 root t. And then negative square root of t times positive square root of t is a minus square root of t squared. Here, 3 root t minus 3 root t is gone, and t squared happens to be a nice perfect square, so I can actually take the square root of it. On the top, I had 24 plus 8 square root of t. On the bottom, I have 9 minus the square root of t squared is plain old t, just like that. Now, a couple of things here. We've talked about simplifying expressions when there's squares and all sorts of things like that. There are some things you can do here to see if there's any like values that can cancel or reduce out. In this case, for example, we could pull a 4 out of the top and make that look a little bit different. But with the pluses and minuses down here, we're really not going to end up with anything that's going to be able to cancel in this particular instance. For this expression, same deal. I have a squared on the top, so what? Don't care. On the bottom, though, I have a square root of x plus 5. I don't like the radical in the denominator, so I'm going to multiply by its conjugate because of the plus there. So instead of square root of x plus 5, I'm going to have square root of x minus 5. If you do it on the bottom, you have to do it on the top, so it's like multiplying by 1. And now I'm going to have to go through and do these multiplications here. Here I have one term by a group, so I'm just going to use the distributive property. The square root of x times the square root of x, we multiply the insides and get square root of x squared. Square root of x times minus 5, we do outsides and insides and end up with a minus 5 root x. In the denominator, I've got to do the whole FOIL out thing. So square root of x times square root of x is square root of x squared. Outside, we end up with minus 5 root x. Inside, 5 times root x gives me a plus 5 root x. And in the last, 5 times minus 5 gives me a minus 25. That is now my whole denominator. All right, let's simplify things as best as we can here. Here, the square root of x squared is just plain old x, minus 5 root x. On the bottom, the square root of x squared is plain old x, Negative 5 root x plus 5 root x are like terms that give me 0 root x, which is great. And then at the end here, I have minus 25. So this looks great. You might be tempted to want to cancel things out, but remember these x's are both next to pluses or minuses. There's no like terms or no greatest common factor we can pull out, so we can't make anything any better to look at factors or anything like that. There's no squareds left in this equation to do things any farther, so that's as far as we can go. And even if this looks messier than this original equation, this is often considered to be the better answer because there's no radical in the denominator.